So good morning and welcome to acetal formation and acetal hydrolysis mechanism day. So remember that I am asking you to know a lot of reactions, at least be able to recognize the changes that they do and be able to apply them in roadmaps. But I'm not asking you to know all of the mechanisms. So from this unit, Unit 4, the mechanisms that we'll be testing on include the formation of acetals, and hemiacetals, and the hydrolysis of, I guess it would have been nice to just put those together. I've thought about also putting in the hydrolysis of imines, the formation of imines. I definitely want to look at that mechanism with you guys, but I'm not thinking that the formation of imines and the hydrolysis of imines will be one you're tested on. There's more to come. That's why I said that the mechanisms testing for this unit include these, because next week we're going to do more mechanisms with our carboxylic acids. All right, well, let's go through the acetal formation that we have here. We've got this 1,2-benzene diol, and we're using formaldehyde to create a cyclic acetal. One thing that I did not mention yesterday, and I would like to mention, I used to create materials where all of these reactions, the 4-coordinate reactions on the back, the ones that form our oxygen groups, like the acetal, the diol, the hemiacetal, and the ones that form the nitrogen groups, the imine, the oxime, the hydrazone, the enamine. I used to make materials that in addition to putting H+ and the alcohol or the amine, I would also put MS. And that MS stood for, so you might see this in some places, MS. And that MS stood for molecular sieves. You guys know what a sieve is? Isn't that what the Grim Reaper holds? Is that a Sith? A scythe. Oh, a Sith is a Dark Lord from Star Wars. What is a sieve? A strainer. So what are we straining at the molecular level? Good morning. This helps us strain out water. You might remember, you're welcome. You might remember that these reactions are very equilibrium based, meaning the products that are formed in acid react together to form the starting materials. So as soon as you form water as a byproduct, and I haven't actually shown that, but notice how the 2 hydrogens from the alcohols are gone and the oxygen from the acetal is gone. So there's a molecule of water that is in byproduct. The acid is serving as a catalyst. As the water and acetal form in acid, they can react backwards. So we add molecular sieves, which have tiny holes. On a molecular scale, these holes can only fit a molecule the size of water. The holes can't fit anything bigger. Something like methanol that has that larger CH3 group can't fit into the pores in these molecular sieves. Sometimes they're called 2 angstrom or 2.5 angstrom or something. That's not how I wanted it. 2 angstrom molecular sieves. It's not something that we have in labs, so it's not something I can even have you experience. I've also heard that sometimes they don't do well in acidic conditions, so there must be some nuance as to how they're used here. But molecular sieves, not something you're required to put, but I want you to think about how pulling out water is going to improve Le Chatelier's principle on improving the equilibrium to form more products. All right, then before we get going, we have to address this issue of H+. H+ can be a lot of different things. It can be H3O+. If you have H+ in water, you have H3O+. The problem is we don't want this reaction to run in water. We want it to be water-free because water ruins the equilibrium. So we don't want H+ to be H3O+ in this case. We want H+ to be an organic acid, a catalytic acid that we can use to run the reaction that won't produce water or doesn't require water. So we can use things like tosylic acid. Tosylic acid, you might remember, would just be p-toluene sulfonic acid, which you guys know how to synthesize. You could start with benzene and methylate it, and then sulfonate it, or start with toluene, which is very common, and sulfonate it. Another one that we'll use here is acetic acid, and we can write acetic acid as ACOH. You guys should be familiar with acetic acid at this point after all the nomenclature work that we've done. Or you can just use H+. The challenge about using H+ is the conjugate base. The conjugate base of tosylic acid is TSO-. The conjugate base of acetic acid is ACO-. But the conjugate base of H+, exactly, nothing. TSOH gives away H+, leaves behind TSO-. ACOH gives off H+, leaves behind ACO-. H+ gives off H+, leaves behind nothing. So when we use H+ as an acid, there is no conjugate base to go pull the hydrogens off during a deprotonation step. And I'll show you guys a version of a mechanism where I use H+, but I want to start by showing you a mechanism where we use something else. Let's start with tosylic acid here. So I'm going to use TSOH in place of my H+. There's this meme that I saw recently. It's the two astronauts standing on the moon looking at the Earth, and the one astronaut is in front and he goes, "Wait, it's been blank the whole time?" And the other astronaut is like behind him. "Yeah, of course." And he says, "Wait, all of chemistry is just acid-base?" It is. The amount of acid-base chemistry that we will see in all of these mechanisms, quite common. We're in acidic conditions. What do acids do? They protonate things. So if you're in acidic conditions, you should be looking for a base that your acid can protonate, because this is the first thing that almost always happens. If there's an acid it's going to protonate something. So let's draw out our reagents. What can my acid protonate? Acids are not very good at protonating aromatic rings. That would require the ring to act as a base, but then something else would have to happen to reform aromaticity. But oxygens are fairly good bases. So what we see happen, oh, and I'm sorry, I think I mentioned this earlier, I like to draw each reagent at each step, even if that reagent doesn't have a step. You don't have to, but I'm going to draw in formaldehyde for that reason here. The alcohols act as bases. No, they don't. I'm sorry. Okay. Yesterday, I had an exercise with my OChem 1 class on feasibility. This is feasible. I'll just show you what I was going to do, but I'm going to have to change it. Don't copy this down. This is feasible. That oxygen can be a base. But these oxygens are nucleophilic. They're not electrophilic at their carbons, whereas the oxygen of the aldehyde is both nucleophilic from the oxygen, but also electrophilic from the carbon. So we only have one good electrophile. The electrophile is the carbonyl, which means the nucleophiles have to be the alcohols. The alcohols will need to come and attack the carbonyl. But if I protonate an alcohol, that makes it a worse nucleophile. Deprotonate an alcohol makes it better, but protonate an alcohol makes it a worse nucleophile. So I messed up. This is plausible that these oxygens could become protonated, but it's not meaningful. Actually, what we want to see protonated at this step is the aldehyde oxygen. Okay, did you guys catch what just happened? I forgot my step, messed up, showed the wrong thing acting as the base. But I tried to leverage logic to make sense of why that was the wrong step, and I corrected for it. When you guys are studying these mechanisms, you can memorize as much as you want to, but if you can't develop that logic, it becomes really hard to check yourself. What if your memorization failed? Also, you don't have to memorize, right? Because you're going to have a small selection of mechanisms to show on the final and 2 sides of a sheet of paper to record example mechanisms. So I'm telling you this now. I'm telling this to the camera too. Put examples of the mechanisms on your cheat sheet and bring them into the exam, but know how to use them. The number of exams that I see where the mechanism page is just blank makes no sense to me, because it is the same steps over and over, and it's the same oxygens playing the same roles over and over. All right, so after correcting for that mistake, I should see that my alcohols are actually completely normal, but what I've done is protonated my formaldehyde. I now have my conjugate base tosylate. What did we say changes for the carbonyl when it becomes protonated? What changes for that carbonyl when it becomes protonated? Boy, I must still be half asleep. I just wrote 2 twice. When protonated, the carbonyl becomes even more electrophilic, becomes more reactive. The partial positive at the carbonyl carbon gets larger, which means weak nucleophiles are even able to attack the carbonyl. And alcohols are considered weak nucleophiles. So now that my carbonyl is protonated, now I can see my nucleophile, my weak nucleophile alcohol, act as a nucleophile and run acyl addition. Now I want you to be careful as you go through these mechanisms because it can be so easy to lose track of things. Lose track of carbons, lose track of protons, lose track of charges, lose track of conjugate bases. Just as you practice it, be looking for each of the components of the reaction. Did it matter which alcohol acted as a nucleophile? No, it didn't. And remember that this is a diol, which means it's going to form a cyclic acetal. But if we had two equivalences of alcohol, we would have just said one equivalence attacks first, one equivalence will attack later. Nothing is happening to the OH bond, which is why that OH bond is still there. I've decided to show both of those hydrogens that were on formaldehyde, but I want you guys to recognize those might just be assumed in a regular bond line structure. All right, well, I've protonated, which made acyl addition easier for my weak nucleophile, but now I have this positively charged structure, and I need to deprotonate. What will be my base in this deprotonation step? Tosylate is my conjugate base. Tosylic acid is my catalyst. So tosylate has to reform. Well, that wasn't in red, but tosylate takes hydrogen away from O. Man, there's a lot of hydrogens on O. How can I be confident which oxygen to deprotonate? How can I be confident which oxygen gives up its proton? Yeah, more positive, more acidic. That's actually one of our rules in Caryo. Caryo says more positive, more acidic. And there's only one positively charged oxygen. Hey, what do you know? I have just reformed my acid. And what should I consider doing in the presence of acid? What I should consider doing in the presence of acid is protonating something. Okay, well, I've got a lot of things I can protonate. Actually, the same number. I've got 3 oxygens that my tosylic acid could protonate. We said last time it was the carbonyl oxygen that got protonated because I want to save these alcohols as nucleophiles. If I protonated this oxygen, would you agree that just reverses the step, which is possible, but just not meaningful to our mechanism? So I'm not going to protonate this. If I protonate the other alcohol, the original alcohol, not the alcohol that formed from the carbonyl, that does the same thing as before, where I actually lose my nucleophile. I no longer have a nucleophilic oxygen. So I'm going to protonate the carbonyl oxygen a second time. That creates a good leaving group. What is typically predicted to happen here is that the leaving group leaves on its own, similar to SN1. But carbocations should be avoided if they can be avoided. You remember how this protonated carbonyl has a carbocation resonance form, but we don't show it because we can avoid having a carbocation by putting the positive charge on oxygen. How can we avoid having a carbocation on that structure? Well, true to the name elimination, in addition to having a leaving group, there's also a pi bond that can form. The oxygen of that newly formed ether, the first nucleophilic oxygen, is able to share a pi bond with the carbon, the CH2, which helps kick off that leaving group of water. Think about your positive charge. Positive charge was conserved, but rather than drawing a positive on a carbon and drawing a carbocation, the oxygen has shared its electrons. Does that look like an ether on the bottom? It certainly looks like an ether at the start, but does it look like an ether at the end? What does it look more like? To me, it looks a lot more like a carbonyl. It looks like a CO double bond. Instead of being a protonated carbonyl, it actually looks like an alkylated carbonyl. It's a carbonyl that has an alkyl group going off of it. And if we have an alkylated carbonyl, then much like a protonated carbonyl, it should be easy to do acyl addition. So we see a second round of acyl addition. What serves as the nucleophile this time? Is the other alcohol. Okay, I did stop drawing the water because that was a byproduct. Is that it? Is that my final product? No, but it's not far. I've not reformed my acid catalyst, and I just have a protonated form of my structure. So the last step in our mechanism is deprotonation. If you didn't catch that yet, we should have an equal number of protonation and deprotonation steps. Every time I protonate, I'll need to follow with a deprotonation. Okay, I have a question. How many bonds to oxygen does the original carbonyl carbon have? Not a trick question. 2. The original carbonyl has 2 bonds to oxygen. How many bonds to oxygen does that same carbonyl carbon have by the end of the mechanism? Same number. Still 2. We've taken 2 bonds to oxygen and we've substituted them for 2 different bonds. Okay, last question. How many of the final bonds to oxygen are bonds to the same oxygen as the initial oxygen? How many of the oxygens in the acetal were the oxygen from the carbonyl? None. Where did the oxygen from the carbonyl go? Left as water. So keep that as a goal in this mechanism. I need to get this oxygen of the carbonyl. I need to get that oxygen to leave as water. And if I don't get it to leave as water, I've done something wrong in the mechanism. Here's another thing that I've seen. I've seen students that actually, they prefer to write out the mechanism this way. They solve it step by step, which is great because I only started teaching it this way when I saw how helpful it was for students to learn it. But I'll see students get to this elimination step and they don't show elimination. They don't show the ether forming a pi bond. They just show the water leaving and they show a carbocation forming. To be fair, there is a carbocation resonance form. So that's not wrong. It's just not the major product or the major resonance form. And they'll call it elimination despite not looking like what we see elimination look like all through OChem 1. Then they'll call the next step acyl addition, but acyl addition only works if you have a CO double bond to open. That's the definition of addition, is breaking a pi bond. And if you don't show that pi bond forming, this step is no longer acyl addition. If you show it attacking a carbocation, it's just SN1, essentially. It's an SN1 included within this larger mechanism. I can't encourage you enough to show it this way because it is true to what the molecule is doing. The reason that the water is able to leave as readily as it does is because this oxygen stabilizes that positive charge by sharing its lone pair. Questions on the acetal mechanism? Okay, I have a question for you. How would you assign points to this if you were going to grade it? The reason I want you to think about that is because you are going to be graded on this. So I think it's useful for you to think about what's fair in terms of how this is graded. A lot of professors that I've seen teaching a course like this, they'll give a mechanism problem and then they'll say this is 10% of the grade. So the exam is out of 100, this is 10 points. And then they get to grading it and they try to figure out how 10 points applies to this question. I have tried designing that backwards. Look at the question and design the points around it. So I want you guys to consider that. Why don't you talk amongst yourselves if you'd like to be just one big group? A short discussion, no more than 4 minutes, on how you would try and assign points. You don't have to come to an agreement, but talk about what your options would be. My goal with this is that you analyze the mechanism and see all of the parts inside of it. Okay, 4 minutes. I'll be right back, actually. I'm going to grab some water. Give you the freedom to talk or sit in awkward silence. Justice, what do you think?
I don't know. I don't want to say like 7 points because that's a lot.
Yeah.
So.
Because he really likes the arrows, making sure that they're correct.
Yeah,
And each step being correct, I was thinking like 14 points.
I was thinking like half of it is like the right structure, so the other half is like the
share? You want a few more minutes? I didn't give you 4. Sorry, let me just not butt in on your time then. Oh, but I'm not asking you to tell me how I grade. I want you to think about how you would grade this. How would you assign points to it? I'm open to hearing how you think I grade it too. I'm not trying to hide that from you guys either.
I feel like if it was me, I would grade by step. So it would be like a 7 point.
Mm-hmm. 7 steps, 7 points. Figure it out.
And then we were saying like, I think we were saying like split each step up, like for the right structures you get half points, and for the right arrows you get half points.
Yep. So I agree. This is how I have this is how I've landed on grading them. Assign the number of points based on the number of steps. Half of those points go to the structures, half of those points go to the arrows. Although I've noticed like 7 divided by 2 means there's 3.5 points to go to structures and 3.5 points to go to arrows. Some steps have more arrows than others. Oh no, they all have 2 arrows. I didn't notice that. Well, definitely in some mechanisms, certain steps have more arrows. And I thought about this, Layla, which was, do I just look at a mechanism and assign a point for every arrow that should be there? And every charge that should be there? And that the structure has to look right? Because then every mechanism would potentially be unique depending on how many arrows there really are. And not just arrows, some of the steps require that we show a lone pair, some don't. So should I add any points for the lone pairs that need to be there? It's really challenging. Actually, what I feel like I've been running into with assigning the points based on the steps is that then it doesn't break down very easily, because you don't have to predict the first structure or the final structure. And so it always feels like there's a little bit of extra points. So what I've been thinking to do is, you have to draw arrows on the first structure, so there's some amount of points there. Like this is a component. One component is arrows here. 1, 2, 3, 4, 5, 6, 7 places where you have to show arrows. But in terms of structures, you need to draw this structure, which is the same as what you put arrows on next. So 1, 2, 3, 4, 5, 6 structures that you're predicting. You're drawing 7 sets of arrows, but you're predicting 6 structures. So there's not an equivalence between the arrows that you're doing and the structures that you're predicting. And this is where I run into that problem with, if I just say it's out of 7 points, or even if I say it's out of 14 points, 2 points per step in the mechanism. And then it's easy to say 1 point per structure, 1 point per set of arrows, but actually there's a structure missing. So that would mean every single mechanism I grade, you get a freebie. Here's the other problem that I run into in grading these, is how many points to take off per thing that you miss. Like, let's say, yes, I give 1 point per structure and 1 point per set of arrows. If you draw something in here that has slightly wrong arrows, and then it leads to a slightly wrong structure, but it was based on your arrows correctly, what do I take off? Both? Take off points for the arrows, take off points for the structure? Grading mechanisms is perhaps the most challenging part of teaching organic chemistry, because you guys can be so creative. And when I say you guys, I mean students. can be so creative in coming up with mistakes in mechanisms, things that I just can't plan for. And that makes it really challenging then to apply to a rubric, which is why a lot of instructors that grade mechanisms grade very harshly. Is it correct? Full points. Is it incorrect? Probably just no points. A lot of instructors don't know how to give partial credit because it's really hard to figure that out. Okay, well, anyways, I want you to be thinking about this because I'm thinking about it. The more you think about it, the more you think about what really goes into it. Where are all of those arrows that I'm going to be graded on? Where are all of those charges and lone pairs, and what does the structure look like? And if you think about the fact that I would give you half credit for a mechanism just for having the structures correct, you could approach this in a way of, I'll memorize what changes over the structure. I'll memorize that the carbonyl gets protonated, that the carbonyl gets opened, that the ether gets deprotonated, that the alcohol, the new alcohol gets protonated. I'll memorize these changes that the functional groups are going through, and that will give me at least half credit, and then I could reason my way through the arrows that are needed. That's one way to approach it. Okay, one more question here. Where's the hemiacetal? An acetal, a geminal diether, has to form by way of a hemiacetal. So where is the hemiacetal? That is an acetal, sir. Sorry. That's just a protonated acetal. Not definition. Yeah, definition of a hemiacetal. Like, for instance, I would say the definition of an acetal is a geminal diether. What's the definition of a hemiacetal? Good. Geminal. Geminal alcohol ether. So where do you see it, Layla?
I guess it kind of like is there halfway through the mechanism.
Halfway makes sense, doesn't it? Because it is hemi, after all, to the acetal. So could you tell me, for instance, say like at the end of step whatever, that's where I see an hemiacetal formed.
Like the end of elimination?
The end of elimination? I'm
No.
not sure I've seen ether.
Yeah, because there's another one there. Never mind.
Okay,
The
okay.
end of, protonation, right?
The end of protonation.
No, before.
This, you mean the second protonation?
Yeah.
Well, this does have a geminal ether and other oxygen group, but that's not really an alcohol anymore, is it? It's now a protonated alcohol. So if that alcohol weren't protonated, then it would be a geminal ether alcohol, which happens just at the step above it. Here's the hemiacetal. Notice how I left off that other oxygen, that other alcohol of the diol? Of course I did, because that second alcohol at the top is not geminal to anything else. And remember that the acetal and the hemiacetal carbon was the carbonyl carbon. In this case, where we're using formaldehyde, then it's just that CH2 that is the acetal carbon. Here's our acetal carbon. So guess what? You already know how to do an acetal mechanism. You already know how to do a hemiacetal mechanism. You do the first 3 steps of the acetal mechanism, and you have done the hemiacetal mechanism. Good? All right. for our next mechanism, we're going to look at the hydrolysis of an acetal. Remember that an acetal requires two equivalences of alcohol to form. So when you look at the hydrolysis, we should see two equivalences of alcohol. And we do. But they weren't two equivalences attached to the same structure. They weren't even two equivalences of the same type separate to each other, like what we saw in some of our reactions yesterday. Instead, what we're seeing is both a cyclic formation and an intramolecular hydrolysis. One of the alcohols was on the same carbon as the carbonyl. One of the alcohols was not on the same molecule. I don't know why I said it like that. One of the alcohols was a part of the same carbon chain. One of the alcohols was part of a different carbon chain. We saw here how two alcohols can be part of the same carbon chain. We're going to see here how two alcohols can be part of a different carbon chain. Man, you know what? Actually, no, I think I need you guys to do one on your own. You've watched me copy this one down. Here's what I want you guys to do. I want you to take cyclohexanone and using methanol, I want you to make an acetal from methanol. While this mechanism is still up on the board. That way we can point things out and address them as needed. Show me a mechanism for cyclohexanone forming an acetal in excess methanol. Is it clear how many equivalences of methanol you need to use? Is it clear that I didn't say how many equivalences you are allowed? I've written methanol, but you need at least 2 equivalences. Seven steps. Will it take 7 minutes? You got a question, Justice?
Yeah, I think, I'm just curious because I'm pretty sure if I'm doing this right. You form like the protonated ketone carbonyl, and then do you attack that carbonyl with another equivalence of, with a equivalence of CH3OH, or do you attack it with the deprotonated CH3O minus?
How are you deprotonating methanol? How are you getting CH3O minus in the presence of acid? We made TSO minus, so I should be able to make something negatively charged. But don't forget that TSO minus pushes that negative charge through a sulfonate group, so it's not a negative in just one spot. TSO minus is a very weak base. CH3O minus, very strong base.
So you would just draw the arrow from the lone pair of the oxygen to an H to protonate it?
Yeah, if you don't want to use H+, remember that you can just use TSOH in place of that. Or ACOH. You can pick one. Yep. I'll actually show you guys what it looks like when I solve this mechanism. I'll show you what it looks like to do H+, but I just don't recommend it. It's not a better way of doing it. And Brenna, there was a little more information I gave, which was like the mechanisms from this unit that you'll be tested on are acetal formation, acetal hydrolysis. But the H+ in the mechanisms shouldn't be H3O+, because these reactions are equilibrium dependent and we want as little water as possible. So we use TSOH in place of H+, or we use acetic acid, ACOH. And then I told them too that some places you'll see MS next to the acid that's being used, which stands for molecular sieve. And in lab, it soaks up water, which improves Le Chatelier's principle, pushing equilibrium to the products.
Thank you.
Mm-hmm. Whoops. Okay, I found a typo on the roadmaps.
I'm on the right track here.
Good, 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 good. Yep, you're on exactly the right track. No, yeah. Sorry. Good. Show me a lone pair. Perfect. Great. This doesn't follow what we're expecting. It's not wrong for methanol to act as a conjugate base here. Since you've used H+, there's not really a conjugate base. One way you can get around that is by just not showing something bonding to H+. Show the OH bond break, and you're left with H+, right? If the electrons leave H, then it's H bonded to nothing. But if you want to show methanol as a base, that's good. But this is predicted to be a protonation step of the alcohol. So we should say this gets protonated, not that it does a nucleophilic substitution. Also, you went from geminal to vicinal. So you've done this in 1, 2, 3, 4 steps, not the mechanism. We're looking for 7. Good job pointing out the hemiacetal formation. Yeah, you're doing great.
I have a question.
Mm-hmm.
So, I have to get hydrogen to bond here.
Yeah, so I would do that in the first step.
Okay.
Rather than protonating methanol, which was actually the mistake that I made at the start of the class. I said one of the alcohols could get protonated. Do you know in reality when you go into lab and mix all this up, yeah, the alcohol could get protonated. But that's not useful to our mechanism, and we're just showing them what needs to happen for the mechanism to happen. So start with the carbonyl getting protonated. How's yours going?
Pretty good.
Great. Yep, yep. Oops. Good. Now, Jaylee, you're on the right track. And remember that this is the elimination step. So in addition to kicking something off, I want you to form a pi bond. Elimination should form a pi bond. So you see the water leaving, like we had in the elimination step, and then the geminal ether. Mm-hmm. Perfect. Great.
And then the other.
Yep. Exactly it. Close. Just missing something on your last structure there. Keep in mind that you've just gotten here. Where did that OH bond go? You see how you had an OH bond?
Mm-hmm.
You didn't say anything changed. So nothing should change. It should still be there.
Oh, I see.
Right? Like how it's still here.
Yeah, that makes sense.
Good. Who should take those electrons? Why? You think O should take them just because I pointed it out, so it must be wrong. H can take electrons too sometimes. But I think if hydrogen has 2 electrons, it doesn't have a positive charge. How many protons? Right, right. And see, this is why it's useful to have a conjugate base. Something that can go in and say, I'll take this hydrogen, you, oxygen, can have your electrons back. But without the conjugate base, it is really strange to just see the electrons leaving. Good though, you got it. Yours is done, great work. Yours is done? Yeah, it is. If you guys want to make predictions about what happens in the hydrolysis, you're welcome to start there. Just keep in mind, you're going to move backwards through each step. That's the only change. The only thing earlier I think you had it written different. You had OCH3. And that is a better way to draw it because it is O that's bonded. But notice the way that I did it where I drew all 3 bonds coming off of O? Yeah, this is good even. And then with its positive charge. And now we can set it up to be deprotonated. But does hydrogen own the electrons?
No.
Because wouldn't that kick off H minus?
Okay. Oh, so we're doing this.
Right, right. And you've got a conjugate base. You've got something that can come in and remove that hydrogen for you if you want to. But if you don't want to show the conjugate base, it still behaves like this. Yeah.
What does CY stand for?
Can you infer it from context?
No, I keep thinking it's cysteine.
I think, how do the amino acids get abbreviated? Both capital letters? Or both lowercase letters? Or one capital, one lower?
I think there's like a 3-letter code, or there's just a single 1-letter code.
So why would CY make you think of cysteine? That's 2 letters.
I know. CYS, but
I see. Okay, but context. Look at you're shown the products. The products must be in the starting materials. What do you think?
Is it that oxygen of the cyclic structure is throwing me off? It's I don't know where that came from, or where that goes.
So can you find the acetal carbon and figure out where that is in the product? And then there should be 2 alcohols of the acetal that are kicked out during hydrolysis. So where do those alcohols show up? Where were they before? All right, so you guys are pretty well close to finished here. Instead of using TSOH in place of H+, I'm going to show you guys what it looks like when we show just H+ on its own. And I'm going to do this mechanism fully sequentially rather than doing it step by step so that you guys can see what both versions look like. First step is protonation. And there's a lot that can be protonated, but only protonation of the carbonyl is meaningful to our mechanism. Protonated carbonyls are more electrophilic. So we protonate first and then do acyl addition. After my acyl addition, I need to deprotonate the alcohol that just attacked. I have no conjugate base. I have no base that can go in to take the hydrogen away and give electrons back to O. So instead, I just show the electrons going back to O. And what does that leave behind? It leaves behind H+. It's a weird thing to show. It really takes practice to get used to drawing H+ as a byproduct. Then we protonate again. Once again, there's a lot of things that can be protonated, but only one thing that can be protonated meaningfully in our mechanism, and that's the alcohol that was the carbonyl, because now I have water attached to my structure, and I can kick off water. The ether is helping to kick off water because the ether forms this pseudo-carbonyl. Because I've formed this pseudo-carbonyl, I can once again do acyl addition, this time with my second equivalence of methanol. And then there's multiple ways to consider this last step. Once again, my conjugate base is nothing, so I could just say the OH bond breaks to O. That's all I have to say. But I do have something different than last time. I have this molecule of water here, so I could show water serving as that conjugate base. Which would leave me with H3O+, but again, that's the same as saying H+ and H2O. Okay, congratulations, that is your acetal mechanism, 7 steps. I want to point out, actually, Jay Lee had something interesting. Jay Lee at this, the first deprotonation step said, what if my second equivalence of methanol was the base and became a protonated methanol? Because now there's water on that methyl carbon, and that water could be substituted off by this alcohol. So Jay Lee actually took a bit of a different route and said, what if I do substitution? Which is not wrong, and this is an important thing. This is a plausible mechanism. This is a route that most of the molecules likely go through, but it's not the only possible way that you could see this transformation occur. But I don't want you guys to feel like you need to reinvent the wheel with these mechanisms. In fact, what I want you to show is that you can recognize the steps and show the mechanism that we've gone through in class. So Jay Lee's ended up being like 4 steps, which was not 7 steps, which is a good indicator that somewhere along the way, something happened. All right, now it's time for our hydrolysis mechanism. Before we start, look at the starting acetal. Find the acetal carbon. Look at the product. Find the acetal carbon. Where is the acetal carbon in the product? You didn't find it? Uh-oh. Where is the acetal carbon in the product? No, it shouldn't be hard. Any guesses?
Is it carbonyl?
Yes. The acetal carbon is the carbonyl carbon. That's the whole point of the transformation. We take a carbonyl, and then it's no longer a carbonyl. So, what Justice was asking earlier was, in the structure we're given, something is written as CY. And then in the product we're given, nothing is drawn as CY. But I want you to recognize that CY was part of the acetal group. It was one of the ethers. And it was not part of the ring, which means it itself was part of a different carbon chain. And in the product, we have two different carbon chains. One alcohol is attached to the carbon chain, one alcohol is not, and it's attached, it's just its own ring. CY is an abbreviation for cyclohexyl. So in this case, cyclohexanol or cyclohexyoxy. Okay. How many steps in the hydrolysis mechanism? Oh, the same number, because all we're doing is reversing the process. We're just taking the product and we're going backwards. Our first step, well, our last step in forming the acetal was deprotonation. So our first step, it has to be the reverse of that, protonation. Actually, I want you guys to notice, all the steps are reversed, but they're reversed diagonally. So our last step was deprotonation, so our first step is protonation. Number 6 was acyl addition, so number 2 is elimination. Number 5 was elimination, so number 3 is acyl addition. Protonation and deprotonation, protonation and deprotonation, acyl addition and elimination. What's the opposite of an acyl addition? Elimination. What's the opposite of elimination? Acyl addition. We're just going through these reversed. All right, so protonation are, we need to protonate something. Last time we said, start by protonating the carbonyl carbon. Start by protonating the carbonyl oxygen. There's no more carbonyl oxygen because it's an acetal. So which one should I which oxygen should I protonate first? Doesn't matter. If we were to take this version of the acetal and hydrolyze it, which of these oxygens needs to be protonated first? Doesn't matter. Which of these oxygens needs to be protonated first? Doesn't matter. Which of these oxygens needs to be protonated first? Doesn't matter. So I'm going to take the easy way out. Do you know what? I don't, in this, yeah, actually I think we do. I'm going to take the easy way out. I'm going to protonate the oxygen that is part of a separate molecule. And that way I can just kick off that other molecule. And I won't have to draw this long carbon chain the whole time. I can just draw a ring. So I'm going to protonate this oxygen connected to CY. I could have protonated either one. Now that I have that group protonated, I have a good leaving group. But these leaving groups would leave carbocations, and if I can avoid a carbocation, I should avoid a carbocation. So when this group leaves as an alcohol, the adjacent ether donates electrons in. Remember, your elimination step should see the formation of a double bond. So far, water is not playing a role. Justice, do you see now how CY can represent cyclohexanol? Okay. Now that I've got this pseudo-carbonyl, my weak nucleophiles, water, can do acyl addition. When I see that positive charge on my structure, I'm looking for a way to take a hydrogen off of it. If there is no way to take a hydrogen off, it is what it is. But if I can find a way to remove a hydrogen, then I can do a deprotonation step. And that's what we'll see here. Now that water has attacked, I can remove a hydrogen, deprotonate that water. Pamela, anything of interest with this intermediate here? Could we call it anything? That's a hemiacetal. So we're halfway, right? I guess when we're doing it backwards, halfway comes a little later. Going forward, the hemiacetal was at the end of step 3. Going backwards, the hemiacetal is at the end of step 4. Well, now that I've reformed my acid, I should look for a way to protonate something. If I protonate that OH, I just reverse the step that I just did. So I'm not going to protonate the OH, I'm going to protonate the ether of the acetal. Did you get that other mechanism? Okay, great. Great work. Did you keep in mind where the carbonyl carbon is? That carbonyl carbon is the hemiacetal carbon. Did you keep in mind where the carbonyl oxygen was? In the formation of the acetal, we said the carbonyl oxygen leaves as water. So in the hydrolysis of the acetal, the carbonyl oxygen should have come in as water. Hey, there's water's oxygen. Water's oxygen. Water's oxygen is this alcohol, which means in my elimination step, I want that OH to become a carbonyl carbon. So I'll use that in my elimination. Carbonyl, or this OH forms a carbonyl, kicks off an alcohol, and then I have a final deprotonation step. Now, at this point, I can draw my carbon in a different carbon chain if I want to, rather than keeping it in this conformation that looks a lot like the structure before. I can draw it in a new conformation where it looks like the lowest energy conformation. First thing we did was protonate the carbonyl to form the acetal. The last thing we do is deprotonate the carbonyl to hydrolyze the acetal. I don't know what it is about me and mechanisms, but I talk through them so much, it takes a lot of time. It takes a lot of practice, though. You got to practice these. Go home tonight and do them on your homework. A couple of things. I made a mistake on this roadmap. We talked earlier about having more time at the end of class to let you guys keep working on these. Do you want to do that? Or do you want me to just put up answers for them? I'll post these answers to Canvas then. I'll take pictures of them and upload them as an answer key. But I'll address the issue that I made. And it actually applies with acetals here. A use of acetals. Acetals can serve as protecting groups. Imagine that I have a carbonyl in my structure, but I want to make a Grignard. I can't make a Grignard in my structure because it will just attack the carbonyl in my structure. So instead, I take the carbonyl, turn it into an acetal, so it's not a carbonyl anymore. Acetals can't go through acyl addition. They're not acyl groups. I've essentially protected my carbonyl from nucleophilic attack. Now I can make a Grignard. So on the very far right side where you're going up, I just can't really show this going up. And I guess I'm going to just give you the structure as well. So it has you brominate an aromatic ring, and then it gives you CH3OH in H+, methanol. Remember, that's a weak nucleophile, so it is not going to be substituting the aromatic ring. The H+ even gives us indicator that it will be an acetal formation step. Ketone gets turned into an acetal. Then the next step, this is where I messed up. The next step had written a ketone in a condensed molecular formula, and then it just said excess H3O+. This is where I messed up. I didn't actually make the Grignard. So what I'm going to ask you guys to show is actually first Mg, and then these other two steps are second and third. What does the magnesium do? Really, this should have just been an extra step longer. The magnesium interacts with that aryl halide and turns it into a Grignard. If we had added Mg at this step, Grignard on one molecule would attack the carbonyl on the other molecule, and we'd polymerize our molecules. That's not what we're going for. So we don't want to attack this carbonyl. We make it not a carbonyl. We turn it into an acetal. Then we create a Grignard, introduce a carbonyl, and then have excess acid, because we know that acyl addition with Grignards requires that acid workup to generate an alcohol. So the carbonyl we introduced, CH3 carbonyl CH3, acetone. The Grignard will attack that carbonyl and make a tertiary alcohol. The excess acid protonates that step and hydrolyzes the acetal. The acetal served as a protecting group. The acetal protected the ketone from acyl addition until the Grignard was consumed, and then the acetal was removed. So that was a correction I wanted to make on there. Did you guys have any questions from the rest of the roadmaps that I can answer? And I'll post the key later today. Justice, I thought you had one. Yeah, it didn't make any sense. That's fair.
Well, I just didn't even know where I didn't get that far. But.
Evan, did you have any questions on it? Jaylee? I saw you guys made some progress on it, but no outstanding questions keeping you from finishing? Okay. Then I will upload this answer key. What I want to do then with the 8 minutes I have left, I want to talk to you about the imine formation and imine hydrolysis. First, can you guys tell me what reagent needs to go over the arrow to form the imine? No? What reagent is necessary there to go from cyclopentanone to the imine that we see? You don't have to give it a name, but you could say what is needed. Nitrogen is needed, for sure. And what else should be bonded to that nitrogen? Definitely another carbon. How many in that carbon chain? A methyl, yeah. So a nitrogen with a methyl, but a nitrogen with one bond is a 2- nitrogen. So anything else that nitrogen should come with? One hydrogen. So nitrogen with 2 bonds is a 1-. How do you expect to have a 1- hydrogen in H+ conditions? Would be tough, right? So we need 2 hydrogens. NH2CH3. The 2 H's are going to leave with the oxygen of the carbonyl because this has a water byproduct. And the reverse reaction just needs H3O+, which is what you get with water and acid. Is forming the imine the same number of steps as forming the acetal? No, sorry. Is forming the imine the same number of steps as forming the acetal? It's not. Can you tell me what step is missing from the formation of the imine against the formation of the acetal? What does the acetal have extra that the imine formation doesn't? Yeah, acetal has an extra acyl addition. Doesn't that make sense? Look, we're left with a type of a double bond still. We're not consuming that double bond again, unlike we did with acetal formation. All right, well, first step is acidic conditions. Something needs to get protonated. And what I should expect to get protonated is my electrophile's oxygen. So I'll protonate the carbonyl, which makes this an even more electrophilic carbonyl. My amine can serve as the nucleophile in the same way that my alcohols served as the nucleophile. A little bit different. Instead of oxygen having 3 bonds and a positive charge, now it's nitrogen with 4 bonds and a positive charge. But what's not different is the deprotonation. Nitrogen becomes deprotonated, gives up H+, or if a conjugate base is nearby, conjugate base takes away that H+. So I've done protonation, I've done acyl addition. So far, everything looks the same. We could call that structure the equivalent of the hemiacetal to the imine. We could call that the hemiimine. That's halfway to an imine. It's a geminal etheramine. Well, I'm in acidic conditions again, so I will protonate my oxygen for the second time. This should feel so familiar to what we've just did, because now I have this good leaving group, and on the same carbon, I have a nitrogen that can share electrons to make a double bond. This is the place in the acetal mechanism where we would expect to see a second nucleophilic attack. But we don't. We don't see another nucleophilic attack. We don't see acyl addition occur again. This time, all we see is deprotonation. You see how close we are to that imine, right? Water can serve as our base, or nothing can serve as our base. And we form the imine. If you substituted the methyl for an OH or an NR2, nothing changes. It's just that the nitrogen has a different set of things coming off of it. The entire mechanism stays the same. But if instead of NH2CH3, we used something like NHCH32, then we see the final deprotonation step changes. And this is where I want to leave you, I don't want to leave you here. I want to show you that last step. But this is where we'll leave today. Next week, I do want to compare again some of these nitrogen mechanisms, but we're going to compare them in the context of carboxylic acids and their derivatives. Can you all appreciate that if I took the CH3 and I replaced it with OH, then I could really just draw OH at every step here and nothing changes. It just gives me a different derivative. It gives me an oxime. If I took CH3 and I replaced it with nitrogen bonded to two other groups, then I show nitrogen bonded to this nitrogen with two other groups, nitrogen with two other groups, and I get the hydrazone instead. I could show the CH3, I could show the OH, I could show the NR2, the imine, the oxime, the hydrazone. But if my amine is secondary, that's when things change here. Because all of these other groups had that hydrogen for nitrogen to have deprotonated. This secondary amine has no hydrogen for nitrogen to deprotonate. So instead, we see deprotonation from the carbon adjacent, the alpha carbon, which helps form a carbon-carbon bond and gives electrons back to the nitrogen. It still satisfies the nitrogen's charge, but it does not form an imine, it forms an enamine. Why does the enamine form? It forms when nitrogen doesn't have enough hydrogens to lose. Thank you guys for your time. You have everything that you need to be able to solve the homework for aldehydes and ketones, which should be due tonight, if I'm not mistaken. So I'm hoping to be able to grade it tomorrow. I've got a busy day tomorrow. We're doing interviews for our hiring position. I'll do my best to get those homeworks graded tomorrow, but it's not really a rush because the unit test isn't for another week. And next week we have another homework assignment. That's the only reason I want you to be paying attention to it. Okay, thank you guys. Have a good weekend.
Can I ask you, so this 2A for the homework, did I do that right?
Great. Yep, that's perfect.
Okay, and then that one, I think I should be able to figure that one out now.
Good. Good. I hope you can. I think you should too.